So let's talk about the Arrhenius equation and its relationship to catalysis. We haven't talked about catalysts yet. Last time we talked about catalysts, we said that they speed up a reaction, but that's all we said. We didn't say anything else beyond that. So this slide is what you saw last time. All right, this is the amount of energy required for the reaction to begin. We call that the activation energy, right? And as we increase the temperature, we have more particles that are able to jump over that hurdle, right? So if this is the blue temperature, low temp, red graph, high temp, right? We've got more particles that are able to get over that barrier. And this is one of the reasons why we say rate increases with temperature. Remember the reaction, the rate constant is temperature dependent, right? Constant K is temperature dependent. So at a new temperature, you will have a new rate constant. And that's what the Arrhenius equation tells us, okay? We're looking at the relationship between temperature and rate constant. That's what the Arrhenius equation tells us. The Arrhenius equation will be given to you on your reference page. Okay, I'm not going to make you memorize it, but you do need to be able to do the arithmetic. So the natural log of K2 over K1 is equal to activation energy over R, where R is a constant. Okay, it's not the gas constant that you remember from Chem 1. We use this one in Chem 1 as well. We calculated root mean squared velocity. Do you remember that from Chem 1? Well, that's the same R that you use there. Okay, activation energy over R times 1 over T1 minus 1 over T2. Okay, and 1 and 2 are not relevant. It doesn't matter which one you assign as T1, which one you assign as T2, so long as the K value goes with it, right? So K1 needs to go with T1, and K2 needs to go with T2. So it's not like this is a final minus initial thing. It's not, you're just assigning, okay, you're temperature 1, you're temperature 2, okay? And just make sure that your K goes with the correct T. So if I say K at 500 Kelvin and K at 900 Kelvin, make sure you plug in the 500 Kelvin with this one and the 900 Kelvin K with this one. Okay, make sure that they match. You can't just arbitrarily plug in the Ks. And then EA is activation energy, and it needs to be in joules. Why can it not be in kilojoules? Well, because R is in joules per Kelvin mole, right? So if your activation energy is in kilojoules and your R is in joules, you're going to have a clash. That's going to create a problem. So make sure that if your activation energy is given to you in kilojoules, you convert it to joules so that it'll be compatible with R, or convert R to kilojoules, either one. These need to be the same, okay? Because otherwise they won't match. So this allows us to predict, if I know K at one temperature, what's my new K going to be at a second temperature, right? Or what temperature should I raise this to if I want K to become this value? Okay, that's what the Arrhenius equation is letting me do. So why don't you try this one? At 550 degrees Celsius, the rate constant for a reaction is 1.1 liter per mole second. At 625 degrees Celsius, the rate constant is 6.4 liters per mole Celsius. What's the activation energy for this reaction? I'll pause the video for you to try it. Get as far as you can, at least. All right, let's go over this one. So we are calculating activation energy. If we've got two temperatures and two values of the rate constant, what's the activation energy? So we take the, now again, don't forget temperature needs to be Kelvin, okay? And the T1 and the K1 need to go together. So these two are a pair and these two are a pair. Okay, you can't just plug them in arbitrarily. Make sure that you're plugging the correct T and the correct K in together. So we take natural log of 0.6 over 1, essentially. Do this component. So EA over 8.3145 times this. So I got 1.4 times 10 to the 5th. Did you? Or if you converted it to kilojoules, that's fine. You good on how to do this? Ready to try another one? Here's another one. First order reaction has rate constant of 4.6 times 10 to the second, negative second, excuse me, and 8.1 times 10 to the negative second at 0 and 20 degrees Celsius. What's the activation energy here? Check your work. We're again solving for the activation energy, same variable as we did last time. We have to convert Celsius to Kelvin, right? We need to keep our pairings together. So 4.6 times 10 to the negative second needs to go with the 273 and vice versa for the other one. So I got 1.9 times 10 to the fourth. Did you? 1.9 times 10 to the fourth. Keeping two significant figures. You agree? All right. So again, I will give you the Arrhenius equation. You just need to be able to use it. And I could ask you to solve for any one of these variables, right? I could solve for the new rate, solve for the temperature. I could ask you to solve for any one of those variables. And I know that there's one like this on the homework as well. Okay, so like I just said, as temperature increases, rate increases, right? We increase temperature, we increase rate. That's what the Arrhenius equation shows us. But what if we want to increase the rate without raising the temperature? I mean, there are a lot of times that you'd want to do that. Think about digestion, right? Digestion, if left to its own devices, if you just throw your food in with some acid and say, here you go, and you let it run at 37 degrees Celsius, it's going to take forever to break your food down to a level that your cells could use. So why would it be bad to increase the temperature significantly in your gut? Why would that be bad for, homeostasis? That would be bad. That would denature all your proteins in your cells at the stomach, and it would be bad news, right? So there are a lot of times where we want to increase temperature, want to increase rate, but we don't want to bother the temperature. Okay, and so that's where a catalyst can come into play. Now, here's a definition that I took directly from a very common biology textbook, which will remain anonymous. All right, we're going to protect the guilty here. This is a direct quote from that biology textbook. And this is why I want to say words we use in biology are not necessarily the same in chemistry. A catalyst is a substance that speeds up a reaction without being consumed. That's directly from a really common biology textbook. And I want you to be very, very careful with this definition, because I know a lot of people in this room are biology students. I know a lot of you have taken it, or maybe you're currently taking it now. The part where it says without being consumed, well, that's really misleading, okay? Because what do we know about collision theory? We know that particles have to collide, they have to touch, right? And then there has to be some sort of change, yes, as a result of that touching. So a chemical catalyst does get used in the reaction, okay? It does collide with those reactive particles, and it does get used up. But then it gets produced again at the end. We're talking about a chemical catalyst. Now, if we're talking about an enzyme's a protein, they're a different story. And that's probably what your biology book is referring to, okay? Because a lot of times, the enzymes in your stomach that speed up digestion, those are proteins. Okay? Those engage with your molecules differently than a chemical catalyst does. Okay, so just make sure that you're really, really careful with definitions like this, because a true chemical catalyst does get used and then it gets produced again. So we're going to differentiate between a chemical catalyst and an enzyme in a minute. So a catalyst work, how does it work? This is important that you know this. How does a catalyst increase the rate? What does it do? What's so magic about a catalyst? Well, a catalyst offers an alternate pathway, okay? So if you have an uncatalyzed reaction, it goes step 1, step 2, step 3, right? Well, maybe with a catalyst, it's only a 1-2 step reaction. Or it might still be a 3-step reaction with a much lower activation energy. So it gives you an alternate pathway with a lower activation energy. So it speeds it up, gives you a new mechanism. It actually changed the mechanism. Okay, and I use this as an example because I have kids, and so it's very relevant to me, right? My 4-year-old wants to put on his own shoes. That's great. I'm all about the 4-year-old putting on his own shoes, right? I've got 2 4-year-olds. So when I'm in a hurry, I'm like, guys, we are like 15 minutes late, right? The activation energy for both of them to get their shoes on the right feet, and right? That's very time consuming. It's got a high activation energy because they've got a lot of work to do. Whereas I'm like, oh, just come here, let me do it. If I'm being, if I'm planning ahead and I'm giving myself lots of time, then I can let them go uncatalyzed. But if we're in a hurry and we're like 20 minutes late, I'm going to catalyze that reaction, right? We're going to get a lower activation energy. So a catalyst does change the mechanism, okay? It does change the mechanism to one that's got a lower energy barrier. So here are some data, right? There's a catalyzed pathway versus an uncatalyzed pathway. Notice delta E is still the same. What's different is the activation energy here, okay? So here's exothermic reaction with a catalyst. Again, delta E doesn't change. Activation energy is what's changing. And here's an endothermic reaction with a catalyst. Again, delta E doesn't change. It's the activation energy that's changing. Okay, make sure you understand the difference here. A catalyst does not change delta E. It's not going to change delta E at all. It's only going to change that activation energy because it offers a different pathway. Here, go down this way, lower activation energy. Or you can stay uncatalyzed and go down this way. All right, and just so you know, a catalyzed reaction may occur in more steps than the uncatalyzed one. That was what I was saying a minute ago. It might take more steps to do the catalyzed reaction, but overall, the activation energy is still going to be lower than your one-step uncatalyzed. Okay, so don't be thrown off by the fact that a catalyst might add an extra step to your mechanism, but the net overall activation energy is still going to be lower. So that's what I was just saying, alternate pathway. Now here's where we have to differentiate from you biologists. Okay, an enzymes are proteins. Okay, they're large macromolecules, and so I think what biologists are most commonly referring to when they say that they don't get used up is the enzyme, the protein, is not like being destroyed and then remade. Okay, so the enzyme, the molecule that comes into the enzyme is called the substrate. So it goes in, this enzyme breaks the bond, forms the bond, rearranges the molecule, whatever, and your enzyme stays the same. Okay, so I think that's what your biology book is referring to. Now, a chemical catalyst works differently from an enzyme. So I'm going to show you an example with a chemical catalyst. Where it is. But that's the number one misconception, is that they don't take part in the reaction. That's not true. Even with an enzyme, it's still taking part of the reaction. It's still touching it. Okay? That's not a true statement. That's false. Now let's also differentiate between a catalyst and an intermediate, because if I give you a mechanism and say, which one's a catalyst, which one's an intermediate, you need to be able to differentiate between those two. Okay? A catalyst gets consumed at the beginning and made again at the end. It'll cancel out of your net reaction still, right? Because if it's at the beginning and it's at the end, it's still going to cancel out of the overall reaction. But an intermediate is a link between two elementary steps. They'll also cancel out, but it's the location of where they are, right? Catalyst is used at the beginning, produced again at the end, it's going to get canceled. Intermediates are links in between elementary steps. Do you see the difference between a catalyst and an intermediate? I'm going to show you some mechanisms here in just a second, and I'm going to ask you to spot which one's catalyst, which one's intermediate. Actually, right now. So look at these. This is a mechanism. I didn't give you the overall reaction. Look at this and decide who's the catalyst, who's the intermediate. Have you figured it out? What's the link between step 1 and step 2? NO2, right? Without NO2 being produced, step 2 couldn't happen, right? So does that make NO2 a catalyst or an intermediate? It's an intermediate, right? Now a catalyst is required to get the thing going, right? Because it lowers the activation energy and then it's produced again at the end. So who's the catalyst here? NO, right? This is the catalyst. Right? So there's your catalyst. It was used at the beginning and consumed and produced again at the end. When we add these up, it's going to cancel out of the overall equation, right? And then the intermediate is a link between two steps. Again, when we add these up, it's going to go away. Okay, do we see the difference between a catalyst and intermediate? Okay, one's used at the beginning and produced at the end, whereas one's a link between steps. Okay, let's just test our vocab skills. Let's see how much vocab we know. All right, in general, the rate of a reaction will not be changed by altering the surface area of reactants, volume of the vessel, concentration of the reactants, or temperature of the reaction. Will not be changed by what? Heard someone say something. Volume, right, the volume of the reaction vessel, right? Whether your reaction is taking place in a 50 milliliter beaker or a 400 milliliter beaker, isn't going to change the rate, right? Surface area, that goes back to how much touching goes on. Concentration goes with how much collision's going on, and so does temperature, right? K is temperature dependent. Good. The average kinetic energy of the reactants can be increased by increasing concentration, increasing surface area, increasing temperature, adding catalyst, or any of these. Which one is it? There's only one correct answer. Which one?
E.
The surface area?
E.
Oh, E. Any of these. Okay, that's one guess. Anyone else have a guess? Thank you for sharing. I appreciate you very much. Anyone else have a guess? That's a good guess too. Thank you for sharing. The correct answer is temperature. Right? What's the relationship between kinetic energy and temperature? Temperature is a measure of kinetic energy. It's a direct measurement of kinetic energy. That's the definition of temperature. Temperature is a measurement of kinetic energy. Okay? Those two are directly linked. So the way we increase kinetic energy is by increasing temperature. Okay, this one's got a lot of reading, so we're going to summarize it. Kinetics is studied at 25 and then again at 50. Which would explain the results? Rate at 50 will be twice that at 25 because we doubled the temperature. Rate at 50 will be faster than 25 because more molecules have sufficient energy to react. Rate at 50 will be slower than at 25 because molecules will be moving too fast to collide effectively. Or rate at 50 will be faster than 25 since activation energy is lower when you increase the temperature. If I put this on a test, I can tell you with about 98% confidence what students will pick, and it's not the right answer. What do you think 99% of my students pick? A, they do, they pick A. Why? They say, okay, we doubled the temperature, therefore we're going to double the rate. But does that doubling the temperature guarantee that the rate is also going to double? No. B is the correct answer, right? We have more particles moving with enough kinetic energy to overcome the activation energy barrier, but we cannot say with certainty that it's going to be double. Okay, we can't make that assumption. 98% of students pick this answer. This one's the correct. All right, this is the last one. Here are two equations in a mechanism. And what I want you to do is, for each one of these, tell me, is it a reactant, a product, an intermediate, or a catalyst? So what's peroxydisulfate? Reactant, product, intermediate, or catalyst? It's just a straight up reactant, right? What about iodide? Reactant, product, intermediate, or catalyst? I think I've got the answers in here. Yeah, I do. Reactant, product, intermediate, or catalyst? It's just a reactant, right? What about sulfate? Reactant, product, intermediate, or catalyst? It's just a product, right? What about I plus, iodine, cation? That's an intermediate, good. And what about I2? Iodine, the element. It's just a product, right? Is there a catalyst in this reaction? No, no catalyst. If there was a catalyst, where would it be? It would be on this side here, and then where would it be on the end? This side here, right? It gets consumed here and reproduced here. Good. Okay, so I've got some enrichment problems that we're going to do. I'm going to pause the video. You're going to do these with a friend or by yourself. Okay, so what we did here on campus, for those students here in class, is we did some problems. So I passed these out. These are also posted on the course website. mechanisms enrichment and not Arrhenius equation, mechanisms enrichment and catalysis enrichment, I think is what it's called. But anyway, if you're watching this online, just pause the video and try these two questions. Well, few questions, I think there are 4. So here's question 1, mechanism. Here are 2 questions to answer. Pause it, hit resume when you're ready. Here's another question. Pause the recording, try it for yourself, hit resume when you're ready. And then here's the last problem. Here's the coordinate diagram, and then here are the questions. So I'll zoom it out a little bit. There we go. Again, pause the recording, try it for yourself, and then hit resume when you are ready. So now we're going to go over these problems here in class so that everybody gets the answers. Okay, so this following mechanism is proposed to explain this reaction. All right, so the first question asks, determine the rate law for each elementary step. How do we do that? It's based on the what? What's the M word I'm looking for? Molecularity, right. So rate equals K, what for this one? K1. It's just NO2 squared, right? Because NO2 times NO2 is the same thing as NO2 squared. If you wrote it as NO2 times NO2, that's fine, right? It's not wrong to say X times X or X squared. They mean the same thing, right? So if you wrote it as NO2 times NO2, that's fine. But you don't have to. And then the rate for the second elementary step, rate equals K2, what? Concentration of N2O4 times concentration of carbon monoxide. Do we agree? Both of these are unimolecular, bimolecular, termolecular, what? These are both bimolecular. Good. So there was part A. And then part B. The experimentally determined rate law is rate equals K NO2 squared. Okay? In the lab, you find that step 1 takes longer than step 2. So which one of these is the rate determining step? Step 1 or step 2? Step 1, right? So this is the rate determining step. Okay? And based on this information, is this an acceptable mechanism? Well, we have 2 criteria, right? You have to what? The 2 steps in the mechanism have to add up to the overall equation, right? And what else? What else? Kind of move my screen a little bit. This is our rate determining. So the 2 criteria is these 2 steps have to add up to the overall reaction, right? And the experimental rate law needs to match the mechanism's rate law. So we need to find out, do these 2 things apply here? So when I add these 2 equations together, what do I get? NO2 goes bye-bye, right? N2O4 goes bye-bye. So that leaves me with what? NO2 plus CO produces NO plus CO2. So does the first criteria check out? Does this mechanism add up to the reaction I'm interested in? Yes. So adds up to overall reaction. That's criteria number 1. Yes. And then, does experimental rate match mechanism's rate? That's question number 2. Well, what is the experimental rate? Here's the experimental rate. Based on my mechanism, what's going to be the rate for this mechanism? This one or this one? The top one, right. So now you just ask yourself, do these 2 things match? K NO2 squared, K NO2 squared. Yes, they do. So is this acceptable? Yes. Does acceptable mean that it is the best mechanism? No, it just means that it's acceptable, okay? Make sure you understand the difference between acceptable and best, right? Any questions on this one? We good on this one? All right, let's do the next problem. Here's problem number 2. I'm just going to go ahead and put it on its own page so that I've got plenty of room. Okay, following mechanism is proposed to study this overall reaction. Experimental data reveal that steps 1 and 3 are fast, and step 2 is slow. So, fast, slow, fast. Okay. And so, let's go through the questions here. Intermediates. Do we have any intermediates? Oops, it's on page 1 still. Do we have any intermediates? We do. We have, remember, an intermediate is a link between 2 elementary steps. So this is an intermediate, right? Because without N2O2, can the second step take place? No, it can't, right? And when we add these up, that's going to get crossed out. So N2O2 is an intermediate. Is there another one? N2O, right. Again, because if this doesn't get produced, step 3 doesn't happen, right? When I add these up, they're going to get canceled out. So those are my intermediates. Do I have any catalysts? Do I have any catalysts? No, we don't have any catalysts. How would I know if I had a catalyst? All right, if I had A plus, and then over here it's produced as a product, that's where a catalyst would be. But I don't have any catalysts. So no, there are no catalysts in this problem. Okay, let's write the rate law for each elementary step. Rate equals K1 NO squared. Do we agree? Rate equals K2 N2O2 times H2. And then rate equals K3 N2O H2. Do we agree there? Those are the rate laws for each elementary step. We just looked at the steps, their molecularity, wrote it from there. Do we agree? Do we agree? All right, so just look up there. For the balanced equation, let's add it up. So when we add these things together, let's see, N2O2 goes away, N2O goes away. Anything else we can reduce? I don't think so. 2NO plus 2H2, right? Because those can be combined. Those can be combined. Produces N2 plus H2O. So there's my overall reaction. 2NO plus 2H2. Oops, that's not a plus, that should be equals. Equals N2 plus H2O. Okay, just for curiosity, let's see if the mechanism adds up to the reaction I'm interested in. 2NO, 2H2, N2. Oh, there should be a 2H2O, right? Because those two add up. 2H2O. So yes, my mechanism does add up to the reaction I'm studying. That's a good thing. That's probably going to be a question we'll be asked later. All right, what's the rate determining step Step 1, step 2, step 3, or I don't know. Step 2, right, is the slowest. Step 2. All right. Now this is kind of getting on my nerves, so I want to keep the mechanism here, but I want all these questions gone. There we go. Ta-da! Okay. Now it's cleaned up a little bit. The experimental rate law is K NO squared H2. All right, so we already know that the mechanism adds up to the overall, right? So mechanism adds up. That's true, we already know that. So does experimental rate match mechanism's rate? That's question number 2 we need to ask ourselves to determine if this is acceptable. Now this one's a tough question. I want to see if you got it. The answer is yes. Did anyone come to that conclusion? Anyone come to the conclusion that it is? Let's talk about why the answer is yes. The experimental does match the overall, the mechanisms. And here's why. Which step is my rate determining step? Step 2, right? Step 2 is rate determining, right? However, what has to happen before step 2 can occur? Step 1's got to happen, right? And step 1 is really fast, right? So, in other words, without N2O2, step 2 doesn't happen. And step 1 produces N2O2 very, very quickly, which means I can substitute this in for that, because this happens very, very quickly, and this is the rate determining step. And this step immediately precedes this step. Do you see why I'm able to do this? Because without step 1, step 2 doesn't happen. And step 2 is what determines how fast this overall mechanism occurs, right? So if this one occurs super, super fast, that means that I can plug it in here as concentration of N2O2. Because where is the concentration of N2O2 coming from? It's coming from step 1. You see? So that means, therefore, we can plug rate 1 in for concentration N2O2, which means rate equals K2 NO squared H2, right? Does this match this? And the answer is yes, they do. Now, the only way we're able to get away with this is because this step immediately precedes this step, and because this step is the slower of the two. Okay, if this were vice versa, we couldn't do that. If the slowest step was step 1, we couldn't make this substitution. Okay, but because step 1 is really, really fast, and step 2 is what determines the overall rate, I can say with confidence that the concentration of N2O2 is the direct result of this being fast. Therefore, I can plug this in as concentration of N2O2. Does everyone see how we got away with that? I couldn't plug in, say, this for this, because this is the rate determining step, and this one's really fast. So that one was a tricky one. So does it match? The answer is yes. So is it acceptable? Yes. Again, accept doesn't mean that it's best. It just means that it's acceptable. That's like saying, which kind of car is the best car to get from point A to point B? Well, there are a lot of acceptable callers. The best one is a judgment call, right? There are a lot of criteria to factor in there. All right, last problem. Use this diagram to answer the questions. Okay, so we need to decide if this is exothermic or endothermic. I guess I don't need my notes because it's right in front of me. Exothermic or endothermic? It is endothermic. Okay, why is it endothermic? Products are at higher energy than the reactants were. Let's label our reactants. They are here, and our products, they are here. And activated complex, remember I told you that's the same thing as transition state. Same thing, some books call it an activated complex, some books call it a transition state. They're the same thing. Change in energy. How do we get change in energy? That's this value right here, right? Delta E. It's final minus initial, so 100 minus 50, right? Do we agree? Activation energy is the energy that the reactants to the top gives us. So activation energy is 250 minus 50, so that's 200. All right, let me erase these equations and these questions. There we go. That's what we just did, right? Activation energy is what we just did. How much energy is released or absorbed? Well, we know it's being absorbed because it's endothermic, right? If delta E is positive, is endothermic. So therefore, 50 kilojoules absorbed. And how much energy is required? That's just EA. So there you have it. Any questions on the back, on the reaction coordinate diagram? All right, well then that's where we will stop.